Start streaming here. All right, folks, I'm going to show you my lack of ability with multi-level models. So I want you to understand that these are very hard for me. I'm going to try to go through an example that Lisa put up. This mirrors her example that goes with lecture 9, the last lecture of your class, this is chapter 9 in her textbook. So Lisa, if you wouldn't mind, when I go through stuff, this is literally taking her syntax, which was in SAS and M+, and converting it to JAG so we can talk about this.
Can you give them my example of those?
I do. I have your example. Her example is in our course folder under this longitudinal example 9 folder itself. This is all the files.
Yeah, did you give them the Word document?
I thought I did.
Let's see.
Well, give me a moment.
That Word document has everything sort of organized and annotated.
It is
You just had it. That right there.
this right here?
Yep. It's pictures.
Let me,
His SAS can make pretty pictures too, it's not just all. As can Excel. I know that's like sacrilege, but
Excel is literally the worst program in the world.
Oh my god, I hate it so much.
hallowed ground, here we go.
Before I started doing statistics, like, I hated Excel
But when you
so much.
collaborate with other people on papers who don't do statistics, they don't know how to do anything. And if I give them the chart in Excel, they can edit the titles, they can edit the legends, and I don't have to do it.
Find better collaborators.
No! Boom.
I'm gonna tell them.
I'm gonna tell them.
Hey, hang on just folks, I'm gonna commit this real quick.
Oh, I can tell the story about the data.
Yeah, go for it.
So these are fake data based on real data. Well, they are.
They're real data. Fake real? No?
This came from my Penn State days as a postdoc. I was in the human development and family studies area, and people studied all kinds of parent-child relationships. And so the story here is that we have adolescent girls measured on risky behavior as the outcome. That's the left scatter plot here. It's sum of basically all the things you don't want your girls doing: smoking, drinking, skipping school, shoplifting, unprotected sex, all that fun stuff. The next one is a average on a Likert scale of 1 to 5 of items that measure parental monitoring at the same ages. And then that's the cross section of the two, where it's monitoring by risky. So then the question is monitoring useful in preventing risky behavior? That's sort of the general idea here. Because somewhere between negligence and helicopter parent, right? That's the sweet spot of monitoring just enough but not too much.
So I'm gonna grab, I tried to do this with some plots in ggplot, then I gave up. But this the blue line, I didn't get the color for each person's line and the aesthetic and gave up. But these are the 3 plots with a smoother. Borrowed some of Lisa's text. So let's go into what we're trying to do here. What we're gonna do is take, the real outcome we're after is the risky behavior at each time point across time. I'm gonna keep looking at Lisa for approval.
And it follows a fixed quadratic
Actually,
random linear tree.
Would you like to come and talk about that? No.
Yeah.
So here in the analysis model itself, for level 1, we're going to put, so the problem with this that takes it away from that case where we could just person mean center our way out of and put monitoring in to predict risky, is that monitoring also has a random linear time slope to it, right? So here, the level 1 variables, we're going to have monitor itself have a growth model. So we'll have a placeholder for intercept, a placeholder for slope. And for both of those, they're going to have a random intercept, random slope. That's just it. We're not going to have any other prediction going on. So that's the level of monitoring each girl is going through at each age in the study. Age is a time variable centered at age 18. Then for risky behavior, we're trying to predict it with, we have its own random intercept right here. Actually, we have a placeholder for intercept, a placeholder for slope, the time slope in this case. And then we have the quadratic effect of time slope here with the placeholder as well. And at level 2, for risky, we're going to use the parental attitudes, or no, childhood attitudes.
Mom's attitudes about smoking and drinking measured at age 12.
Okay, so when the girls were 12, you took parental attitudes toward smoking and drinking, centered it, and you're going to use that to predict each person where each girl's intercept for risky behavior might be. The random intercept right here, I guess, variance. And then we have a slope for the same thing. We're going to use parental attitudes at age 12 to predict each person's rate of change across time with a random slope, excuse me. And then finally, for the quadratic effect, it's fixed. There's no random quadratic on this.
And in the previous chapter, I had tested the effective attitudes and the random slope, and they weren't necessary, and so that's why they're not there. And same with monitor. Monitor didn't need any covariance, didn't need anything quadratic, so this is where we ended up.
Okay, so thank you. I appreciate that. So a couple other things with this that we're going to set up a little notation-wise. This is sort of mixing notation a little bit, but because we have these two outcome variables, and they both have error, we're going to allow those errors to be correlated or have some type of dependency. And so the way we notate that, we say each of these errors, or the vector transpose, follows a multivariate normal, mean zero, but it has a covariance matrix that I'm going to call R. And why am I calling it R? Because I love SAS. And the SAS users guys, they call that R. Right? Level 1 error. Residual variance in the diagonal, residual covariance in the off diagonal.
So this model doesn't have monitor predicting risky, they're just both covariate.
That's right.
So
That's right.
that one's coming.
This one's coming, that's right. They're allowing them to covary, and there may be a message there in the covariance. Second, because we have, for each person, 4 random effects, right? A random intercept for monitoring, a random intercept for risky behavior, a random slope for monitoring, a random slope for risky behavior. We take that vector, transpose, say it's multivariate normal, mean zero, and its covariance matrix is G. Right, so if you're following along in multi-level land versus factor analysis, right? This is like the closest psychometric model to this is a CFA. This would be our phi matrix. These are the factors. This would be our phi matrix with factor correlations. This would be our psi matrix for effectively our item residual variances, but we've constrained all those to be equivalent, right? So each item doesn't have a different unique variance or residual variance. So that's where the crossover happens. Okay, so to code this in JAGS, we're going to create what's called a composite model, right? We're going to take each of the level 2 models where the placeholder variables at level 1 are given, and just plug the right-hand side of the level 2 model into where the placeholder might happen to be, right? That's all it's doing. The reason for that is in JAGS, we have complete control over each of the parts of the model. And so, but JAGS doesn't have a level 1, level 2 syntax. Basically, we have a variable, we have an outcome, we have to give it we have to predict the mean of that thing with everything that we have simultaneous. So, the composite model for monitor, here I took the random intercept, or the placeholder for intercept, substitute with the level 2, same thing with slope, right? And the same thing goes for risky, where we take the placeholder for the intercept, placeholder for slope multiplying the time, placeholder for the quadratic slope. Right, so I did that because to make this analysis work, again, we need to put all of that on a single line. When we get into the JAGS code, we're going to have the monitor variable, the risky variable, and just like we did in the regression part of the course, we're going to give each of it a mean, and that mean is going to come from this part, right? This is the conditional mean. Conditional on, we would say the factor, right? U, the two U's. This is the expected mean of monitor for a person, right? And then the same thing for risky. This is the conditional mean. Everything but error is the conditional mean as well. So that's why we're doing it that way. Now, there is a little bit of data setup that we have to do to get this into JAGS. Although these data are awesome in many ways, in that they're simulated.
They're very well behaved.
Meaning every person gave data for every occasion. Even though the occasions weren't identical in time, So for instance, there are 7 observations per person, and there are always 7. That's not always the case, particularly when we have clustered data. So I set this up to try to be a more general version. So if you have observations that don't have all those cases, you can change it however you'd like to. But here, we need the total number of level 2 observations. That's what I took. And then I'm going to get, this is where I'm going to flip back and forth between the code so I can show you the objects. Here, we get to the number of level 1 observations per level 2 unit. So this is the number of observations, and technically speaking, I could have done this for both x and y. I should have done it for both x and y. I didn't. I should have, but here's the person observation. Basically, everyone has 7 observations. They're all there. Finally, so we're going to put this data into JAGs. The data look like this. This is the other part that's a little bit different in JAGs versus all the other multi-level software. Multi-level software is kind of interesting because this having to convert from wide to long, this is stuff that, remember homework 0 or homework whatever, homework 1 where I had that wide to long crap? That shows up because depending on the software you use, the format of the data input has to be one way or the other. JAGs is sort of really cool because it's like, I don't care. You build the model. What do you want me to do with it, right? But so in that regard, what I'm going to do is keep the data as they are when they came in. And if I can show you those data real quick. Chapter 9 data, here we go. All right, so right here, the data are what we call stacked or long format, where each person's occasion has all the data on one line. So the person 1 has 7 rows of data, and then the occasions are 12 through 18, age 12 through 18. And they have the risky variable, they have the monitoring variable, which is actually monitoring centered at 3. They have their age and parental attitude at age 12, right? So what I'm doing here, what I need to do here, because it's not always the case, although these data are well behaved, it's not always the case that each person would have 7 observations. If this were clustered data, right, we wouldn't have, there's no way in chance we'd have like perfect class sizes in every school if we had children in classes or something like that. We need to tell JAGs which row of the data to look for these observations. So I created a matrix to do that. And that matrix to do it, I'm calling it obs row, which is, I managed to make it with 1 line of code, which made me really proud, but makes it very dense. But basically it's this, right? So here, each column is a person, and each row is an observation. And this is basically going, when we go loop through things, we're going to loop from 1 to the number of observations within each person. Right? So if we only had 5 the first time, it would have been down here. But this tells you which row of the data that observation came from. Right? So that 7 that we saw before is the index for us to loop through each row here. And then the people, the n, is looping through each column. And when we put the 2 and 2 together, we'll cover everything. If I had missing data for a person, with this matrix would just have NAs for where they'd be missing. And the number of rows in this matrix would be equal to the size of the biggest level 2 unit that has the biggest number of level 1 observations, right? Person with the biggest number of occasions.
As an aside, can you walk us through briefly that S-apply or the L-apply syntax?
I'll try.
Yeah.
Okay, so here, the key up here, to get the number of person observations, what I needed to do is search our data for whichever column where the person ID was equal to a number, right? So I'm going to loop from 1 to 200. There are 200 observations here. And in all of the cases where the person ID is equal to, let's say take number 1, right? For all the cases where person ID equals 1, this is going to tell us where that's true or where it's false. And this length statement says how many trues are there, right? So this is basically telling me how many observations in that data row there are. Now, I wanted this to happen over 1 to 200, so instead of giving it a loop, I used lapply, which said, I'm going to put my looping variable here as x, and I'm going to go and give it my own function I specify. So for every x, go and tell me how many times I see a true in that data where that's true. Now the typical object that returns from lapply is an R list, which means it's a kind of an interesting structure. It doesn't map well onto JAGs. So I needed to unlist that, and the unlist function ended up giving us just this, what R calls an atomic vector that had each person's observation. So that's function one. Sorry it's embedded like that, but is that cool?
Yeah, for sure. And what lapply basically does what in general? Or
lapply, for some, it's a loop function, right?
so it's like loop apply basically.
That's right. So for something over here with x, it can be an index like this, 1 to n. It could be another list, right? So for every element in this list, do this.
Sure.
Oftentimes, we might use a regular function in R like the mean, right? If I put mean here, mean of x, what it would do is give a person mean. But instead, we can define our own function with this syntax here.
Cool.
Give us what we want.
And what is sapply compared to lapply?
sapply is effectively lapply, but it does things in a matrix form. So what I had to do here, the only difference between this set of code is instead of saying the length, this is just telling me which rows contain that person's observation. And instead of having them in a big list, I wanted to have them in a matrix.
Sure.
So sapply allowed me to create a matrix of that same thing. So basically it's going to loop over all of the people in the data, the person's IDs, and it's going to return which row numbers of the data set happen to be true where the person ID is equal to that number in our index. And it's just going to sort it in a matrix that's, each column is where which loop function of x happens to be. Sound good? So they do work substantially faster than the for loop. They're also substantially harder to get into your head. But once you land on it and you have like a data set that's 300 million cases, like the for loop can take a half hour to run to do this. The sapply and lapply take like a minute. Like it's a real quick speed up in time.
It's surprising the difference is that substantial.
I didn't realize this until I worked at the DLM project in Kansas, and we had tons and tons of data, and it was just getting anything done was really, really slow just to loop. So most of the time in a class like this, it's overkill. So I tend to not do it in class, but I wanted to, I don't know, I was just trying to.
And some parallel computing based on the
So it parallelizes. Okay, so there's a thing in does it actually, I thought R was single core unless you get a parallel package, so.
yeah, there are several parallel.
Oh, that's right. Yeah, there's a par lapply, there's a par sapply.
Yeah.
Yes. So some of the parallel packages will allow you to take the same loop, because there's nothing that says we have to go start at 1 and do 1 first and then 2 second and then 3 third. Basically, we can do 1 through 200 simultaneous.
Yes.
Spreads it out across the cores.
And then it brings it back and gives you the object. That's right. Thank you, Jihan. Thank you. Sorry. Not in this code, but if you load a different package. Okay. So the other thing I'm going to do is create a data matrix. Sorry, any other questions? All right. I'm going to create a data matrix that's just X. I'm doing X because X is, it's kind of funny. It's X right here, but really they're also Y, depending on what we do. So I just call it X. It's just our risky variable and our monitoring variable, right? So it's just those two columns from the data set itself rather than passing all the data that we need. Okay, going back to this. So putting this in JAGs, this is where it's really fun. Depends on your definition of fun. So we know to make this work that what are the distributions of the data? It's multivariate normal, right? And the multivariate normal data, though, we have to give it something for R, right? The R matrix is our covariance matrix. That's going to have, the inverse of R is going to have a Wishart distribution for a prior, right? So we have to set up the Wishart priors, and that's what I did here. And this is really bad form, but I'm giving the initial R prior effectively an identity matrix. 1's down the diagonal, 0 in the off diagonal. The smallest number of degrees of freedom I can give it. And the same thing with G. 1's down the diagonal, smallest number of degrees of freedom. 0 is now diagonal. Okay, so let's work backwards here. Our observations are x. I should have made this y. I don't know what the heck I was doing. Oh, I know. I was distracted. And so here's x right here. This is going to be for each person's row of the data. There's 2 observations. There's the risky and then there's monitoring, right? So now that's going to be multivariate normal. There's a mean vector that has the same row with 2 columns, which is our conditional mean for the model. And then there's an R inverse, which is the inverse R matrix. So now we have to go and load up this mean vector, and that's where the model comes in. This is the fun part. So the model for risky shows up here. The model for monitor comes second. Technically, I could have done let's talk about monitor first. It's a little bit easier, right? That was the x variable we're talking about here that has the random intercept, the random slope. Here, I tried to keep it multi-level as much as possible. This first part, this mean for it, comes from the part that's the intercept, the random intercept part, and the part that's the slope, the random slope. So the second term is multiplying the age variable, which is data we're going to input. Okay? Any questions? So every step in the chain, we have all these terms saved in JAGs. It's going to create a mean value for each person at each time for monitor. Plug that into DM norm and get a likelihood out of it. For risky, we do the same thing, but risky is a little bit more complicated. We have the intercept placeholder. Here we've got attitudes showing up, right? Here's our random intercept. We've got the linear slope placeholder. Again, we've got attitudes showing up. We have a random slope, linear slope. That multiplies our age variable. And finally, our quadratic slope. This is running on, it's a little too wide here, but the quadratic slope is right here with our quadratic fixed effect age squared. Questions? Lisa, what do you think of this?
I'm just following the mean back is like the predicted,
That's right.
level 2 and fixed effects thing.
That's right. Conditional mean
Right.
of the observation at a given time point. So we're looping over each person and each person's set of observations across their time.
I see, and then it goes down into the thing where level 1 gets put on the variance.
That's exactly it. Other people with questions? Okay. So next we have to go and give priors to each of these terms. There's the R inverse, there's the U's, and there are the gammas. So for U, let's start with that. For each person, U, which has there are 4 random effects, is also multivariate normal. It's going to have, I'm going to give it a mean, but I'm going to fix its mean at 0. I could have just put 0 there. I should have just put 0 there. And then we have a G inverse. That's the G matrix. That's the random effect variance covariance matrix. So the hyperprior for U has the mean set to 0. And then we have our Wishart for the G matrix. We have our Wishart for the R matrix. And so these are the inverse G, inverse R. But then I'm going to take the inverse of them to convert them to the G and the R. And why I like this is because I do love Guns N' Roses.
Welcome.
G and F and R. That's how, whenever I teach like SAS notation, I think of that. Sorry, this is, those of you who don't know this, good. Keep it that way. If you don't know what I'm talking about, don't waste brain cells and space in the head. It's precious real estate.
G, D, F, and R.
Yes. There we go. So now we have all of our fixed effects. I'm giving it a D-norm for each of these again. And just like in the regression thing, I'm making it a mean of 0. I'm making a very wide or very small precision, meaning very wide variance. I'm trying to make it not, now it's not as wide as we saw before, and that's because some of these models are going to be really hard to estimate. So I cut it down a little bit. So what do we need to give for data? We need to give N, which is the number of level 2 units, number of people, X, which in this case was our Y, sorry, person observation, obs row, sorry, this is the number of time points per person. This is which row each time point occupied in our X matrix. Our prior for R, prior degrees of freedom for R, our prior for G, prior degrees of freedom for G, and then our attitude variable and our age variable.
And generally speaking, what's a good way to figure out what always needs to go in that list?
Everything, if you're really have a complicated model, every time you write a line here, write a line for the likelihood here, specify your priors, and then goes directly down here.
Sure.
So it's everything that's referred to in the JAGS text that you're not wanting it to go and estimate.
Sure.
And even with that, though, it's not easy for me to tell you what happened.
Sure. Yeah.
Okay, I'm going to keep. Yeah, sorry. Go
I
ahead.
assume it yells at you if you leave something off.
Yes. This variable is not given. So
You just go add it to the list.
That's-
See if that works.
okay, I can give you like the philosophical version, but then I can give you how it really works,
Sure.
and that's how it works for me.
absolutely.
I code the model up and like, oh yeah, I didn't do that. Or what's worse is I use the same name twice.
Sure.
Which now I have done that this semester too, right? So
With this last homework, I was doing the posterior derivatives, and I was trying to pull out the proper columns. I'm like, okay, go grab things with pattern A. I'm like, there's an A.
theta.
There's
Yes.
I'm like, okay, I'm gonna grab these and then just grab the ones I want.
Yeah, that's
Yeah,
exactly
that
it.
worked okay.
That's exactly it. Yeah, it's very. If you're going to code this, if you want to make a package that makes the user not do this, you could probably find very easy ways, but there's some key decisions you have to make to automate it. All right, so we're going to use parallel JAGs again, and I'm going to put all this in, all the terms in. We're going to run a chain length of 15,000 iterations. Why I'm doing 15,000? It's a little bit bigger than normal. And that's because this also had a little bit of a problem. I actually found more than just a little bit of a problem on the next models, in that when it says Burnin for R to JAGs, that is not Burnin, by the way. That is adapting. There's a difference in JAGs between Burnin and adapting. If you adapt for 3,000 and you have a model with conjugate priors, which I actually believe our model has, it doesn't do anything. It's not adapting. And why do I say that? Because I would come out and I would look at the chain, and because the variance component, there's not a lot of data to do a lot of the variance components. We're talking about variances of some things that are, 200 observations, but they're really complicated in how they work. 200 observations for the variance of the slope of people for 200 observations is really hard to do. So there's some wiggle in the chain at first. It's burning in. There is some time it takes to converge. And every time I would change Burnin, I get the same plot all the time. Right? So I went through the R to JAGs. The manual says it's Burnin. But in the Burnin line, here, I'm going to show this to you. This is the part of why it's frustrating. Here, I even have it up from this week, this last week. When it tells you what Burnin, it says length of Burnin. If it's 0, it will run 100 iterations for adaptation. And that's your only clue. You don't mean Burnin, do you? You mean adaptation. What's the difference between Burnin and adaptation?
Is adaptation the one where it's like it goes a little bit and you want it to be like 43% accepted? Or whatever?
That's it.
That's
So Burnin is technically happening while you're adapting. But if you don't have anything to adapt, if you have a Gibbs prior for everything, a Gibbs sampler for everything, you're not going to move the chain along any. And in this case, I believe we have conjugate priors for everything. So I change Burnin, I'd plot out my chain, and the same, like for the same seed, the same spike at the beginning, the first 2,000 iterations was there, regardless of Burnin. I was getting mad. This is Sunday when your friend was over. So I was like, so I came off as a real big, well, I'm usually a real big antisocial prick. That's just,
He's irrationally angry, don't mind him.
yeah, he's just muttering to himself in the office. Anyway, it was frustrating. So we will fix that a little bit later on in code.
Speaking of homework, I think I saw some of that because my trace plots didn't look like actually my trace plots to look.
That's right. No, that frustrated me very much. So I've been telling you things I didn't. So anyway, let's talk about convergence real quick. Here we have R hat values that look pretty good. What's that?
Oh, my coffee's gone.
Oh no.
It made me really sad.
Oh, I'm sorry. Our hats are pretty good. Look at some chase plots of R. This is our R matrix. So you'll note here with these trace plots, there's something going on at the beginning. And that's real And this is the thing I was telling you about. If I change the amount of burn-in, if I change the length of my chain, the beginning of these trace plots are always the same. That's bad, right? Those observations right there should not be there. And so I had to go a little bit deeper into the code to figure out how to do this. And I used the window function right here. So what I ended up doing was running a 15,000 length chain and set this right here. The starting point was at observation 2001. The end was at 12,000. Well, why is it 12,000? That's because ArtAjax then doesn't say you're running 15,000 chains. It said, no, I cut off the first 3,000. We're going to label the first thing that you see as iteration like 0 or 1 or whatever. Anyway, it's just more frustrating rather than saying 5,000. So I took that and I finally get my results. So when I do that, when I put that through, here are my results. Let's first look, do I have convergence? I don't have convergence on this, but let's talk about what this means real quick. This is where I'm bad. Lisa, you want to help interpret?
What do you want me to do?
Well, let's see here. Let me go this way and code here.
What the numbers mean?
Yeah, you want to talk about,
Sure.
you want to describe them?
Yeah.
Okay. Oh, nope. Sorry, I'm moving around.
By the way, this is job security also, right? You know, you learn the ins and outs of this stuff and someone will pay you because no one else wants to do it.
Okay, so here's your posterior mean. This is your EAP for each
Yeah.
of the fixed effects.
Yeah.
And here you go.
Alright, so O, gamma, OO, these are intercepts,
Mhm.
right?
Yeah.
Given the coding of the model, these are the expected outcomes at age 18. That's when time is 0. In addition, for risky, it is the expected outcome for someone who has an attitude of 4 on average out of a 5-point scale, which was near the mean of the sample. Then we get into the linear slopes. The linear slope for risky is also conditional on age 18 because of the quadratic. So at age 18, let's see that right there. That's the, nope, 01. I want 10.
1-0.
Yeah, that's attitudes. There we go. There we go. Those two. Those are the fixed linear time slopes. Riskies is conditional on age 18. So that is the change in risky behavior per year of age at 18, the instantaneous rate of change in calculus terms. The one for monitor is not at age 18 because it is not in a quadratic model, so it's the highest order term. And you'll note that there is no average change in monitor. However, there are individual differences in change in monitoring, which I think is either 3-3 or 4-4, depending on what you did first. It's 4-4.
4-4, pardon me.
The size is 4-4. Monitoring is a much smaller variance.
Okay.
So,
So the slopes for monitoring is,
on average, there's no change, but there are individual differences in
so
change.
some people are changing this way and this way. Huh?
Like that.
Yep. Okay.
That was what the scatter plot looked like. 01 and 11, those are the effects of attitudes on the intercept and on the slope.
So the higher the attitude,
Yeah,
the
more conservative the attitude, the less bad behavior they have at 18, and the less they had grown in bad behavior during adolescence. And here's my quadratic for risky. Who can I call on? I'm calling on you, Jihan. It's been a while. Okay, what does this quadratic say is happening to the linear slope of risky, which is right here?
So the slope will be which one?
These
Slope
two.
will be
These two.
increased 0.24 every unit increase of quadratic.
Almost twice this, right?
Yeah,
0.28.
0.2.
0.28.
Yeah.
Yeah, so the rule of quadratics, twice the quadratic slope is how the linear slope changes per unit time, because the quadratic is half the rate of acceleration. So I would say that this quadratic slope has made this linear slope more positive by 0.28 per year of age. So it's an accelerated curve where they end up at 1.97. To figure out where they were at each point, you would take that slope and subtract minus 2.8 from it.
0.28.
Or yeah, 0.28 from it to get to the flatter slope at the earlier ages. And the line you made shows that too. It's kind of a zoom. So,
Cool, right?
variance components.
So these variance components you highlighted in your example.
Yeah.
If I can flip to that real quick.
And they came out pretty much the same. Didn't
They did. The numbers were mostly the same. Sorry, let me get this down here.
Yeah, you can show the G matrix. That might make it easier.
But you had highlighted some.
Yeah.
I'm not really going to talk about necessarily what these are, but why did you highlight these?
Because, well, these are the things that running a multivariate model gets you. That these between variable relationships, that's the reason why you would do this, because functionally what he did is run two univariate models at the same time, which is what that's doing. The rationale for doing this is to get those cross-variable relationships. These are all undirected though. There's no like X versus Y, they're related. And the same is true, so this is a residual correlation. That's the offness of your trajectory for one variable at one time, so whether they sort of travel together. And note that it's positive. So more monitoring is related to worse risky behavior at the same occasion? Or is it that your kid is behaving badly, so you kick up your monitoring? X, Y, I
Don't have a design to be able to tell that. We need to manipulate risky behavior.
Or trying to, or the lagged effect.
Okay, never mind.
Last times this.
Sorry, I was thinking of an experimental design. But
But
I guess we manipulate monitoring, but that's much less fun.
Alright, you ladies, start smoking.
That's right.
You ladies, go to the library.
That's right. All right, we're gonna randomly pick who's gonna be in here drinking. I think the IRB would. They're already. The IRB police are coming. They're going to arrest me.
So my point though is like if you look at some of these covariances here, so this is G, this is the covariance between the slopes, or the intercepts, intercepts. So if you are engaging in more risky behavior at age 18 relative to other girls, you are likely to have lower monitoring at age 18. That makes sense, right? Monitoring is supposed to be protective. Likewise, if you grew more in risky behavior between 12 and 18 than other girls, your mom did not grow as much in their monitoring, or they may have decreased. They're at the bottom of the distribution.
I gave up.
So these relationships are negative, as you would expect if monitoring is a protective factor, whereas this one is positive. So there's three different answers as to how monitoring and risky behavior relate to each other.
Shall we delve into how we find those?
But that's unfortunate.
You want to talk about the no, not M plus. I want delving into those relationships, going from the covariance to a directed thing. You want to talk about it? Or you want me to? Yeah, you want to? This is your stuff. I don't. I'm over here being like, huh?
No, so if I want to phrase it as a prediction, which is even if these things are measured at the same time and you can't really say one that came first. For instance, if I want to have a mediation model, or I want to look at how the relationship between monitor and risky varies as something else, like I need to put this into a regression version of the model instead of a covariance version. So we throw in a level 1 effect of monitor.
That's
here.
the full X.
The full X, so this is not person mean centering, this is like the grand mean centering where things are going to become contextual at level 2, because this is all the variance in monitor 1 and 2, not just the level 1 part. We pick up some new gammas here. Do I need to do the subscripts for you guys? Would that be helpful? No? You're good with that? Or don't care? The first number is which beta at level 1 these correspond to. So for instance, in the line for beta, for the risky, for beta 0, everything starts with 0 in that line, because that's the beta it's predicting. Within the level 2 equation, the second subscript keeps track of which predictor of it is. So the first one, sort of the jumping off point, that's the fixed effect that you would start with. Attitudes is the first predictor of beta 0. The second predictor of beta 0 is now a beta. It's the intercept for monitoring. which is defined right here as fixed plus random. The third predictor of beta 0 is the monitoring slope, which is defined up there as fixed plus random, and then we pick up the U. So we're putting these in as fixed effects rather than covariances, which means we could use them to compute direct effects, indirect effects, mediation models, moderation, etc., etc. Likewise, we do the same thing for the risky slope, and then the fixed effect of monitoring that shows up here, we're keeping it as fixed only. It could also be random. It could also have things that interact with it. So that's another limitation of the covariances version. It's very hard to say that a covariance varies systematically as a function of another variable. It's relatively easy to say that a fixed effect varies systematically as a function of another variable. So now we have a fixed effect for beta 3.
Awesome. Thank you for saying that.
Sure.
The reason why I said that, so there's a couple other things I need to go and mention though. So I took that code and being a very novice at these models, just directly implemented them into JAX.
So he, rather than putting the betas in, he's putting what the betas are in here. Which to me is a semantic distinction, but apparently not when you're programming.
That part's okay.
That part's okay.
What I did based on the slides, I didn't know the distinction of how you were treating R differently, because in that level 1, level 2 syntax, you don't specify what the variance components covariances are.
Yeah.
And so I put this in simultaneous to estimating the full G matrix and the full R matrix. Guess what happened? I had effective sample sizes of 3 for the same length of chain. I had parameters that were covariating together. I had a dependency. It was not identified. Basically, these terms are doing the work of the off-diagonal, parts of the off-diagonal for G and R. So that's where I was going to go with it.
Yeah.
Now, sorry, this is where I was going to say this. So here, the R matrix, what we're going to do is we're going to still estimate the diagonal. So this is the residual covariance of risky and monitor at each occasion.
Residual variance.
Sorry, residual variance each occasion, level 1. But the off-diagonal elements we're going to set to 0.
Because that's what that is instead. It's a fixed effect instead of a covariance.
And then for each of the within variable random effects, so these are the random effects for monitor, these are the random effects for risky, those are going to have a covariance between them, right? But the cross-variable covariances, so the covariance between the intercept of monitor and the intercept of risky, or the intercept of monitor and the slope of risky, those are all going to be set to 0. And that's because these other terms right here are picking up where that's happening. All right?
Yeah, it's just like in a path model. If you have an undirected path between 2 variables, you can't also have a directed path. It's redundant.
And so the rest of the model is going to be fairly straightforward apart from that, right? You can imagine what we're going to end up doing. We need to, one last catch for this. I broke the R matrix. I didn't use a Wishart anymore since these are independent. I just used univariate normal, and I did gamma for the inverse residual covariance. So I have this is the priors for that. The G matrices are split though. And now what you're going to end up seeing is most of this is the same. We still have our, but for each observation, I'm doing a univariate normal because that's effectively like saying the off diagonal of the R matrix is 0. I have to do it that way because when I give it a diagonal, well, I don't have to do it that way. I could go and give it the R matrix, do DM norm, but then take 2 other variables and plug them into where it is. But I can't use a Wishart distribution for that R. And I think that would kick us out of being Gibbs, and I don't like that. I like my conjugate priors, right? And so that's exactly right. I wanted this to be conjugate, so I put it both the univariate normal for these. You'll still see, so the univariate normal, there's this one right here for monitor, and there's one for, actually this is risky versus monitor. But then the actual coding itself, now what you'll see for each of the lines where we added that beta, where I have in my line here, instead of just calling it beta, I just put the terms that would be for the beta placeholder there, right? So for instance, on the intercept line, here, bless you. this right here is a beta.
Fixed plus random.
And then this right here is a beta right here, right? And the same thing goes, there we go. Yeah, you have it on both up here and down here. Right?
And this is why monitoring was centered at 3, is I knew it was going to become a predictor, and it's still necessary to have the risky intercept be meaningful.
That makes sense.
Because you can't have a monitor score of 0.
Makes sense. So everything else is pretty much the same about the syntax, with the exception of I split the G matrices into 2, so I have 2 statements. I have the U's for risky and the U for monitor. There's a G matrix for risky, a G matrix for monitor. That now partitions. Now that's one that you really do need to split it into 2 because there's a block in the off diagonal that are set to 0. It's nearly impossible to get that to work. A very patterned covariance matrix is hard to do in JAGs. We still have our other terms. And now, this was the thing that was making me mad, right? Because I couldn't get that part off, right? It takes a little bit of time, but not too many iterations. I mean, that's less than 1,000. That's about 500 iterations. This is the fixed effect of risky, but then it quickly gets its act together. That's how I'll call it. And
It's the fixed effect of the monitoring intercept predicting the risky intercept.
that's right, yeah. Sorry, I said that wrong. Yes. And so here are the results. I did not go and give the Gelman-Rubin, but you can see the Gelman-Rubin for this. Once I cut off that part of the window, we were almost completely converged, and so now we have these results. And now, do you want to talk about where those are different? So this is, what's this? What's the smile for?
Okay, so yeah. So O2 is risky intercept, monitor intercept to risky intercept. Now that looks like a ginormous coefficient, and that looks way too big. That's a contextual effect. That's what that is.
Because we put all of risky in, or all of monitor in to predict risky.
So this is not the between-person relationship among the intercepts. It is the between-person relationship among the intercepts after controlling for the actual value of monitor at each occasion. Mer? So I don't like saying that. So now I'm going to go find, where is 3.0? Need that one. Okay. So this is within, this is contextual. I add them together and I get to what the between effect should be. And you could do that in each iteration, right?
You
As a
could.
linear combination.
Or you can do it on the next set of syntax. No,
Did you make that?
I did. I made the next model. But go ahead.
Oh, okay. So that one is contextual. O2 is. O3 is not. That's slope to intercept between the variables. That one is between. Let's see, 1, 2, that one is not contextual. That one is between. That is intercept to slope. And then this is slope to slope, and that one is contextual.
There it
And
is.
the only reason I figured that out is because I knew what the answer should be, and I knew this wasn't right. And then I sat and tried to figure out why, and when I finally figured out this contextual thing, I was so.
If you compare and contrast this document with M+, you'll see the numbers are pretty close
Yeah.
to the same. And so this is where you're talking about. So now, do we want to fix it? Do you want to make it between?
Yes.
Okay. Lisa, how do we fix it?
One tiny little difference. Well, yours is very big.
Actually, hold on.
That. Rather than sticking in regular flavor monitor, he put in the.
Oh, you don't have the syntax for it here. But yeah,
No, but you can't
the
do it
code.
in a
Yeah,
minute.
there you go.
You can't do
I'm sorry, you
this.
don't have this right here is E.
E.
It's monitor minus your conditional predicted value of monitor, right there, which gives you your within person monitor.
It is the latent variable version of like person mean centering. Like
It's
you're
just-
trying to get just back to the within person residual in isolation and use that as the predictor.
But this is the person mean, but this is also, it's conditional mean because it's conditional on that age slope as well.
Yeah, so
Right.
person mean centering would not be enough because that only gets the intercept.
Unless you
part
say conditional person mean centering,
out.
and then it means everything.
Yeah, but that's not person.
You just outflanked everyone.
Yeah,
Sorry.
So
Okay,
now it should be fixed.
it is fixed. That's the only change.
And this is what M+ now does in their days, is that version of the model, except they don't tell you that they switched the level 1 predictor, so you run the exact same code and you get 2 different sets of outputs because of this difference in what.
I believe if this were R, this is where you'd say, "Oh, you get what you pay for." How much is M+?
$1,000.
Oh gosh. Here, what I created was something called residual monitor. to do that, to simplify it. So this is that part where we take the monitor variable and subtract off what the expected value of that should be conditional on the random effects at each time point. So that's the E term that we saw in the analysis before. Then I put that residual monitor in the place where we had gamma 3,0 before.
And I believe they would call this latent centering, but because the documentation doesn't actually tell you how they do it, I'm guessing.
Oh, you get what you pay for. You'll note there was one time I had to sort of fix, but this was before I forgot. I should have just put that. I could put that back. Now we have a lot more data we're putting in. Let's take a look. Okay, we had this as a problem, but this is the results when we do this. This is actually, pardon me. We'll grab the results for this down here, which are okay, here we go. Now do you want to see those two same variables?
Yep, there it is. So this one was -7, now it's the -4 that it should have been, because it doesn't have to get fixed relative to within everything, and the same is true for 1.3, and that one. Everything's between, and life is simple.
And if you want to do a comparison, on the web version of this, right here. At the end, I made a comparison where what was the mean difference between each of the EAP estimates for everything, and you'll see the ones that deviance is slightly different, but everywhere else, these are the only two that are different. Those same variables. So there you have it. You get what you pay for. Had to do that. It wasn't a setup though. So
just saying, like depending on the type of multi-level structure you have, right? In longitudinal data, just between makes way more sense. In cluster data, usually contextual does.
Mhm.
So it's nice to be able to have the option to get whichever version you think is more useful to you that more directly answers your hypotheses. The difference is that the variance components also should differ in between these two, because if there's a random slope attached to the within person effect. So the only reason that this maps exactly is because there's no random slope at the level 1 effect between monitor and risky. If there were,
oh, we'd be in trouble.
well, the things change in terms of their interpretation.
That's right.
So that this isomorphism only holds in the case where the level 1 effect is fixed.
Right. Yes. Questions? Comments? So this will be the paper. Ask Lisa Hoffman why.
So yeah, multi-level structural equation modeling.
Is it overwhelming to you? I'm overwhelmed. I started.
Can I show them my picture?
Yeah, please.
Where's my handout? Yeah, that one. That. This is the single level structural equation model of the exact same damn thing.
No, it's multi-level.
Nope. This is the same model, which is why I have a hard time saying it's either SEM or it's multi-level, but you can't tell me it's both, because it's not. I can do the same thing in Levon, any sort of single level SEM software. The only catch is that when you set up the model so that, like, if you had the regression directly between monitor and risky, these level 2 effects are contextual. There is a trick that someone came up with called structured residuals to trick M+. And what it involves is taking these residuals and moving them to a new latent variable. Basically, you take their variance, you shut it off, and you assign it to a new variable by saying, like, new variable by old residual at 1. And then if you put the relationship between those new latent variables, that's enough to trick it to make everything else in the middle between. But that new structured residual trick will not work if you want to add random slopes or modifiers. You have to have the old version, which is half contextual, half between.
So I'm biased, but I like the JAG syntax much better. You want to know why? I look at M plus in text and I get mad. Like Lisa was like, well, here, look, it's just doing this. And I was like, I don't know how that goes. I was like mad at her. I'm like, no, I'm not mad at you. I just, at, on, with, by. You know what? It was ridiculous. I'm going to say it.
All the special characters.
Oh, right. We're running out of keyboard space.
No, they did. They used the last one in M plus 8.2. There was one more character. Now they've done them all.
If they didn't use Fortran 77, they'd have to switch to an international character set. No, I don't know.
No, they're
But
going to do wingdings and like.
That's right.
There's nothing left.
Is that a pineapple? How?
Or emojis.
Oh,
right?
that's right. Smiling. Mine would be mad. Oh, there's ways I'm going to get myself into trouble if I go further. All right. So, how many of you, because you're my students and I'm trying to influence you, don't you think this is? Don't you? I'll ask a leading question. Don't you think this is better to know what your model is doing?
Way more transparent.
Way more transparent. Way more transparent.
I mean, it's kind of why I like to use R for almost all the stat stuff I've been doing, because I get to tell it what to do.
Mm-hmm.
And I get only the things I want, when I want, how I want them, right?
Mhm.
It's like Burger King.
Have it your way. Yeah, no, I'm not trying to make this a rip on M+. There's a lot of things M+ does, and getting to this level in R does take some time. It's not like you just off the shelf do that. But I don't know that, like, once you have the basics, I feel like you can quickly dive in and get a model together in JAGS that does some really complex stuff without having the at, on, with, by, around, between, within, under.
Overall. So can I ask a psychometric question?
Yeah.
So we could actually make this a truly multi-level structural equation model. Do you know what these variables are, monitor and risky?
No! Oh! It's just
I know, right?
It's like I just need to like, no!
Okay, Hulk. Take it down a notch. But could we take each
No
of
one's
these
harmed, right?
variables and put a measurement model on them?
Yes.
And
Yes,
then
you
have
could.
that latent factor grow instead?
Yes, you can.
That's a multi-level structural equation model, damn it.
Yeah, just think about how you do that. I mean, you would phrase, you'd have to come up with the trick on where the data are and how that worked. You'd have to have all the observations per person. You may have to input a different matrix of data for it, but you basically have a measurement model in the part of the code. In fact, it might even be across items up here, right? You'd have a factor, and then instead of X down here, it would be factor. There it is, right? So you have but what I'm trying to do with this lecture, even though it's somewhat outside of what we've done in class, is tell you have a lot of the building blocks already to do some really, really complex stuff, even if it didn't feel like it, and this class was sort of a disaster this year. So,
Identification is tricky in those models.
yes, it is.
And you also have to either assume or test invariance of your factor structure across time to make it work. There's two alternative models that would be used in something like that. It's known as either factor of curves or curve of factors. And for items, one seems much more reasonable, but if you're like having different variables that work together to introduce that, you could either put a growth model on like every single item, and then see to the extent to which those item intercepts and slopes are correlated or are indicative of a higher order factor. Or you could make a factor at each occasion and then make that factor grow. The latter assumes measurement and variance for it to work. The former does not. So, if you're concerned about, say some of these items are more relevant for 12-year-olds than 18-year-olds, for instance, if there's non-invariance that you would want to capture so that your latent trait stays meaningful, that would be built into the model.
And you can do that.
Yeah, so in addition to the usual things these sum scores are assuming, unidimensionality, local independence, and equal contribution in terms of equal discrimination. We're also assuming all that is true the same way over time, without testing it.
Wow.
I know, right?
But we could at least get some remedy to some of that in Bayes, if not quite a bit of it. We drag in a few other assumptions. There's ways that you can quickly do an invariance analysis in Bayes, where you have, it's effectively the factor and the observed variable that you're worried about invariance, in this case time, interacting. to predict the outcome at each time point. So you could easily do that as well. So, but there isn't an assumption of sort of the linearity of the prediction there, which may or may not be the case across time. So, if diff doesn't happen in a linear way, it's not just non-uniform diff, because actually it's all non-uniform diff here. It's a non-uniform, non-linear diff. That's the problem. But that's a better way. That's probably harder to go show with small amounts of data than it is with just a linear diff itself. So, all right, what do you think? For a last class, does this tie together a lot, maybe, or I don't know. How many are you going to use Bayes when you're out of here? How many of you have decided Bayes isn't worth the time? Come on. I have no prepositions in any of my syntax.
Sometimes worth the time. I'll give you that.
Okay.
Yeah, there's definitely some trade-offs. I like Bayes from the philosophical perspective. That sits well with me, and it makes some things that we just can't do with ML possible.
Mm-hmm.
But it is very time-consuming and difficult to do what otherwise might be super simple things with ML. And so, in some cases, it might not be worth it because you'll probably get the same answers anyway.
Well, we started the class, the first Bayes thing we have is a linear regression, right? That was pretty...
Yeah,
Yeah, I'll never do that.
No.
no,
But this,
right.
to do this, there are ways, by the way, M+ had made a decision about the ML version versus the not. I believe they could have done a marginal ML and gotten that second model done through using an EM algorithm with a step to, basically the E step to give you random effects. It's not often done in ML, it's sort of an older version of it, one of the 1980s algorithms from mixed effects models, but you could do it, I think. Because you have an essentially empirical mean of each of the person's random effects at that point, so you could residualize if you needed to. There's a choice they made. Yes?
Just thinking, we'll see if that shows up in like 8.5 if they're listening to you.
I want the preposition near. Could you put near into on, at, with? Is it around? Is around in them? Oh, I want around. X around Y. Yeah, that one.
There's X with.
No. Yeah, what's that? That's.
Variable interaction.
I know. All right. I'm going to stop before I don't know. Hey, I want to thank all of you for a great semester. Homework next week, by the way, due on the Friday of next week. Please turn it in to me on Friday of next week, mainly because I got to get your grade in. There won't be any revisions, but just you can do it. I know you can. If you need help, office hours. I had meeting creeps in there, so if you need to meet with me, email me. I will meet with you whenever you want. So no office hours next week, but just by appointment. No official. I'm available for business office hours. Okay. I want to thank all of you for a great semester. If you haven't filled out the online survey for how I did, please do. I know it was not, I didn't live up to the glamour I had thought for the class, but I'm hoping that you got enough out of it that you'll be able to go on further from this. So, thank you.
Thank you.
All right, clapping for you. And thanks to Lisa Hoffman for a great lecture today
Find out.
and for her influence.